We'll get back into where we left off. The example of solving a PDE that is quasi-linear using method of characteristics. Here we have quasi-linear PDE with just an initial condition along the line y equals 1 and x is real. As we showed, the parameterization of the initial data here should be x0 is s, y0 is 1, z0 is 1 plus s. This means that our Jacobian in this case will be x0 prime of s, y0 prime of s, a of x0, y0, b of x0, y0. This should be equal to 1, 2 plus s, 0, 1, which is equal to 1. When we take its determinant, which is not equal to 0, so we have invertibility, okay? The next step is to look at our characteristic ODEs. We're going to have 3 of them. dx d tau equals y plus z with our associated initial condition. Y d tau equals y, corresponding to this coefficient here. Y0 of s equals 1, corresponding to the 1 in our initial condition. And dz d tau equals x minus y, z0 of s is equal to 1 plus s. So this is a little smooshed here, okay? So what did we do in class? We solved y tau equals y first, along with its initial condition of y0 equals 1, and we got y equals e to the tau, okay? Done with that. The next thing we said is that, look, if I add together the ODs for x and z, I cancel out that y and I get d d tau of x plus z is equal to x plus z. So this, along with my initial condition, x0 plus z0 equals 1 plus 2s. This means that x plus s is equal to 1, or sorry, x plus z is equal to 1 plus 2s times e to the tau, okay? So what I can do now is I can say, well, z is equal to 1 plus 2s e to the tau minus x, okay? So this implies that dx d tau is equal to y plus z. This is equal to then 2 times 1 plus s e to the tau, because I just added together the y and the z solution, and then don't forget about the minus x term here, okay? So using an integrating factor, okay, we can get that x of s tau is equal to 1 plus s e to the tau minus e to the tau, okay? The other way we could solve the x and z equations is just by writing them as a two-dimensional inhomogeneous linear system. That would work too. This is just our way of doing it here, okay? So once we have our x solution, we can plug it back in to our formula for z that we had up here. And we end up with s e to the tau plus e to the minus tau. Okay. So what do we do next? Well, we have our solutions. They're sort of scattered over the page here. Here's our solution for z. Here's our solution for x. Here's our solution for y. Okay. We want to do this inversion, okay, of our formulas. The easiest one to do is y equals e of tau. This just gives us the tau is equal to log of y, okay? Because y is away from 0, we're good, okay? We're not gonna run into any issues right around the boundary, okay? How do we get back to a formula for s, though? Let's look at the x equation. So if we look at the x equation, right, we have e to the tau. Well, we know e to the tau is y. So we have 1 plus s times y, and then e to the minus tau, that would just be 1 over y, okay? So if I rearrange things now, if I add that 1 over y to the other side and divide through by y, I can rewrite this as 1 plus s is equal to 1 over y squared plus x over y, okay? I'm almost there. So then I get s equals 1 plus xy over y squared minus 1, okay? So, you know, just a bit of algebra involved, okay? But now I have s in terms of x and y, tau in terms of x and y. Great, okay? So now I plug all this into z, and I get that z is equal to, well, remember it's s e to the tau, e to the minus tau. So those are just y terms there. S is where it gets a bit messy, okay? But nevertheless, if I plug everything in, then I get minus x plus y times 1 plus 2, 1 plus xy divided by y squared minus 2. Or in other words, this simplifies down to 2 over y plus x minus y, okay? So that's my solution then. So I get u of x equals 2 over y plus x minus y, okay? Let's check if this works, okay? So first of all, what's u of x1? Well, that's going to be 2 plus x minus 1, which is equal to 1 plus x, which indeed is our initial condition. What about u sub x now is equal to 1, okay? U sub y is equal to minus 2 over y squared minus 1, okay? So if we plug this in to our PDE, we get y plus u times ux plus yu sub y, okay? So what do I get here? I get just y plus, and then 1 times u, which is 2 over y plus x minus y, plus y times this thing here. So I get minus 2 over y minus y, okay? Well, the y's here cancel, and the 2 over y's here cancel, and I'm just left with x minus y, which indeed is what the PDE requires, okay? So it worked. We got a solution there. So I would encourage you to go through examples on your own. You'll have plenty of time to work on this on the homework. And section 3.3 in Shear and Levy basically extends this to Rn. Okay, so I think as it was asked before, you know, does this work in higher dimensions? It does. The principles are the same. The just, you know, the work gets a little bit more busy. Okay.